Hi guys, good evening. Welcome back to the Haloalkanes and Haloarenes part 2 class. Yesterday we did solve some of the problems, right? We did solve some of the problems and we could understand few important things, correct? We have seen the Hoffman rule, we have seen the Stadtzeff rule yesterday's class, correct? I mean, the previous class. We also tried to understand concepts on the boiling points. Then we did try to understand the SN1 mechanism and how the SN2 mechanism also works. We also understood why haloarenes, they have a lesser tendency to undergo nucleophilic substitution reactions. All these things we have understood. And apart from that, another important thing we also try to understand is about the racemic mixture. We also try to understand about the racemic mixture, where we end up getting a racemic mixture. I mean, with respect to SN1, SN2 mechanism, where we get the racemic mixture, where we get the inversion of configuration. All those things we try to understand in the previous class, correct? Now we will further start discussing related to this chapter problems. Problems related to this chapter. And we are already aware of the substitution reactions, the elimination reactions, the addition reactions. As I keep on telling you people that 11th standard hydrocarbons chapter is such a basic foundation. It's a very you have to understand the complete chapter which will become very, very easy for us to understand the 12th standard chemistry, okay, organic chemistry, right? So saying that, we will continue with the chapter related problems, and here is the first question of the today's class. Okay, so as usual, I always keep giving you 30-40 seconds to first solve by yourself. So even in the today's class also, I'm giving you that 30-40 seconds to start, go through the question. Your time starts now. We have 40 seconds, and after every 40 seconds, I'm going to start solving the problems. Okay, right, your time starts now. Right, so for the following reactions, we see there is an alkyl halide. It's nothing but a bromopropane molecule reacting with the potassium hydroxide. And if you see this particular reaction, you have ended up getting here what? You have ended up getting here an alkene, correct? You have ended up getting an alkene here. Similarly, in the next reaction, so if this is your A and this guy is a B over here, you see now the KOH has been, it has replaced the Br here, correct? So you see the OH group has attached over here, okay? And the third reaction, you see the Br2 has attached to the double bonds. So we have seen here, we are seeing the three reactions here. Hello everyone. We are seeing three reactions here. We need to identify a particular reaction belongs to which category. The A belongs to which category, whether it's an elimination, substitution, or addition reaction. Okay, like that we need to categorize them. Okay, so let us start solving this question. You have 30 seconds. Almost time is up, right? So now if you see this particular question, from an alkyl halide, you end up getting an alkene. So I clearly understand this particular reaction is what? This particular reaction is an elimination reaction, correct? Elimination reaction. Yesterday we did do the dehydrohalogenation reaction, right? Dehydrohalogenation, and we came to understand how an alkene is formed, correct? Beta elimination is the another name for it. So we end up getting here the alkene. So this is your part of elimination reaction. Okay, now if you check this particular reaction, you can understand that the KOH is splitting is what I can say. This is my K plus and OH minus, and OH minus, what it has done, it has replaced the Br, correct? It has replaced the Br. So I understand it's a substitution kind of a reaction, correct? So here I clearly understand this guy follows what here? This guy follows a substitution reaction. Okay, and then what about the last one? Okay, see, in the last one you can understand nothing is getting eliminated, nothing is getting substituted, correct? There is only one thing happening, that is nothing but the addition. The only thing happening is what? Only thing happening is the addition reaction. Now this addition reaction is very, very important. Okay, so if we take as normal example, if I have an alkene here, CH2, and let me say this is my Br, okay, Br2. Normally the Br2 is having which color? It is normally having a reddish brown color. Okay, so this guy has a reddish brown color here. Now, when you react with an alkene, what exactly happens? CH2 single bond CH2, each bromine gets attached to a single, particular carbon over here. Now, what exactly happens to this reddish brown color? The reddish brown color goes disappearing. Discharge of color takes place. Discharge of color. So here you see discharge of the color, correct? That means the reddish brown color disappears. So what it also confirms is this is one of the very well-known reactions in haloalkanes haloarenes, which we have also done this one in the 11th standard syllabus, correct? So this is a very well-known reaction which is known as an unsaturation test, correct? Unsaturation test. I hope everybody remember this one, unsaturation test. So what is this test done for? It is done for the confirmation of what? Or I can say it is done for the detection of or determination of the carbon-carbon double bond. Okay. So based on that, A is an elimination reaction, B is a substitution, and C is what? C is addition reaction. Subhadeep has already given the answer. Very good. So I understand the answer has to be what? The answer is A is elimination, B is substitution, and C is an addition reaction, correct? So fourth is the option. Very good. Okay. So I want everyone to be actively participating, keep solving the answer, the questions. Please put your answers in the chat. Okay. Right then, thank you so much. Let us go for the next question. I hope there's no confusion in this question. Okay, and also no confusion on the concept of the unsaturation test. Okay, normally when you have your practical vivas, there's every chance that external examiner can ask you this unsaturation test question. Okay, right. Let us go to the next question. Which one is the most reactive towards SN1 reaction? I think I've already given you so much details regarding the SN1 reaction in the yesterday's class itself, correct? I did tell you that the molecule having the most stable carbocation. Okay, so the species having most stable carbocation, C plus ion, will favor, correct? Will favor SN1 reaction. That is going to favor the SN1 reaction, and even that the rate of that reaction, the rate of such a carbocation, okay, involving in an SN1 reaction will be much higher. So you need to find here which is the most reactive. Now, if I want to write these structures properly, so this is my first structure, okay. So C6H5CH2Br. So I understand here there is a benzene ring. Then you have a CH2 and a Br. Please write down these things properly, okay? CH2Br. Then if you go for the second option, we still see there is a benzene ring, no doubt in it. There's a benzene ring, but to this benzene ring, you have a CH. Apart from that, it is attached with another benzene ring. Check the structure, okay? It's again C6H5 there. And here we are having the Br, correct? Now let us go to the third structure. If you see the third structure, one by one, I'm writing this structure. So if you see the third structure, you have a benzene ring again. You have a benzene ring, then you have a CH. To this, there is a CH3, then you have a Br, and then coming to the fourth one, the last one. Okay, so you see there is a C6H5, that means we have again the benzene ring. Okay, then you have a C. To this we have a CH3, and again for the same molecule, for the same atom, another benzene ring is attached, and we have a Br over here. Okay, so these are the actual structures given in the question. The actual molecules which are given in the question. So now we need to find out which of the following molecule is most reactive towards SN1 reaction. Now, yesterday I did give you a series, right? I did give you a series that the benzyl carbocation is more stable than the allyl carbocation, correct? That series I had given you, tertiary carbocation, it comes to the last, correct? Now, if you see all these carbons, okay, if you see this carbon, or even if you see the carbon over here, or if you see the carbon over here, or if you see the carbon over here, what I do understand here is they all belong to which category? They all belong to the benzyl category. That means they all are benzyl carbocations, no doubt in it. They will produce the benzyl carbocations. Okay, so all of them are producing benzyl carbocation. Now, we need to check which is the most stable carbocation. Okay, so here I understand this is my primary benzyl carbocation, correct? Then I understand here in this case, I understand it is a secondary benzyl carbocation. Here I shall understand this is also the secondary carbocation, and here it is a tertiary carbocation, tertiary benzyl carbocation. So we already know when there is a carbocations, we understand tertiary is more stable, then comes secondary, then comes the primary, correct? So in this case, what exactly happens? The benzyl carbocation with respect to benzyl carbocation, tertiary should be more stable, then comes the secondary, then comes what? Then comes the primary. That means a tertiary benzyl carbocation should be more favorable to undergo which mechanism? To undergo SN1 mechanism. To undergo SN1 mechanism. So where is my tertiary benzyl carbocation? It is the fourth option. It is the fourth option. Fourth option. Yes, as I already told you, everyone, please actively participate in solving the questions. Please give the answers. Right. So I hope there's no confusion in this question. Okay. So always remember this series, you have to always remember when there is a competition between the benzyl and the allyl, definitely the benzyl C plus ion is more stable compared to what? Compared to the allyl C plus ion, which I had already given you yesterday. Correct? The benzyl C plus ion is more stable than the allyl C plus ion. So the whole factor is what? More resonance stabilization in the benzyl carbocation compared to the allyl carbocation. That's it. Okay. So let us go to the next question. Let us go to the next question. This is a really interesting question. It is definitely a previous year paper question only. It's a really interesting question. I will give you the hint also. You have 30-40 seconds, and I'm also going to give you the hint. This guy will follow, I mean, the reaction will follow Markovnikov rule. It is going to follow the Markovnikov rule. Come on. You have the hint, and you also have 30-40 seconds. Start solving. Be quick, everyone. Be quick. Markovnikov rule. So who is going to answer this one now? Now, first, let me write a 2-butene structure. You have a CH3 here, you have a CH, you have a double bond CH, and you have a CH3. So this is what? This is your but-2-ene structure, or I should say this is your 2-butene structure, correct? This is your 2-butene structure. Subhadeep has given the answer option 3. Let us check it, okay? So now HBr, Markovnikov rule is normally what? Normally Markovnikov rule is nothing but the addition reaction, correct? He follows the addition reaction concepts. So what exactly is happening now? Let me say one of the, I mean, the pi bond, either it can shift towards the right carbon or it can shift towards the left carbon. Doesn't make any difference because both the nature of the carbons are absolutely same. So once this shifting takes place, what I can write here now, CH3, I write here CH plus, then you end up getting a CH with a negative charge, then you end up getting a CH3 over here, correct? So what exactly is happening now? According to Markovnikov rule, or if you just go according to the addition reactions over here, let me say the Br gets attached over here, and let me say the hydrogen gets attached over here. Okay, so the positive charge, because HBr, if I take the HBr, it is going to split into what? You can take it as H plus and Br minus, correct? H plus and Br minus. So what is going to happen now? You see, whichever way you do the reaction, you are going to get one product, nothing more than that. You're always going to get one product. Whichever way you do it, okay, you are going to get one product. But the thing over here is the product what is generated. Check the product which is generated over there, okay? The product which is generated has a presence of which carbon here? It has a presence of a chiral carbon. It has a presence of a chiral carbon, or I can also say it has a presence of a chiral center. That means the product is what here? The product is definitely becoming optically active, correct? The product is becoming optically active. So if a product is optically active, then that means it has every ability to produce what? It has every ability to produce a mirror image, correct? A non-superimposable mirror image. That word is very, very important. Non-superimposable mirror image. That is a very important word. Okay, non-superimposable mirror image is produced. So how do I calculate how many number of such molecules can be produced? The simple formula I'm going to use what? I do see the molecule is what? So now the molecule is like this: CH3, you have a C, you have a H over here, you have a Br over here, then I have a CH2 and I have a CH3. So what I do observe in this molecule is the molecule is clearly unsymmetric, correct? The molecule is clearly unsymmetrical molecule. And how many chiral centers it has? It has one chiral center. That means the N value here will be what? The N value is equal to 1 over here. Okay. So to calculate the number of molecules or the number of possible products here, what I will do, I will use the formula 2 raised to N. Okay. So this is the one which will give you what? Give you the total isomers, the number of isomers formed in the reactions, correct? So 2 raised to N, and N value is what? N value is equal to 1. So it is going to be what? 2 raised to 1. That is going to be 2. So the possible products are how much? The possible products in the reaction. The possible products in the reactions are how much? They are 2. Please make a note. The possible products are 2. So Pradeep did give the correct answer, and even Shobit also has given the right answer. Superb. But I hope now you people have got the concept how to calculate it. Okay. Again, see, such kind of questions you have to be very, very careful, because you need to check whether the molecule is symmetrical or whether the molecule is unsymmetrical, because calculating the stereoisomers, these are nothing but optically active, these fall in the category of what? Stereoisomers, right? So calculating stereoisomers, there are different formulas. For unsymmetrical, there's a different formula. For a symmetrical, there is a different formula. Again, when you go to a symmetrical molecule, if the molecule is symmetrical, okay, then it depends on whether the chiral centers are even numbers or the chiral centers are odd numbers. Okay, so here the molecule is unsymmetrical, so it is very, very simple, 2 raised to N. If it is symmetrical, then you need to check the chiral centers, whether they are even or whether they are odd. Okay, so based on that, the formulas will be given. Okay, I mean the formulas are present. Apart from that, you should be also knowing that just when I say stereomers, when I say stereoisomers, we are actually calculating their what? We are calculating the number of enantiomers. We are also calculating the number of mesomers over there. So if that formulas you have to be learning. Okay, you should be knowing those formulas. Okay, right. So we are going to move to the next question. As usual, you will get 30-40 seconds. Start your answers. Shobit, Subhadeep, and all the else who are involved. You have 30-40 seconds. Now, Friedel-Crafts reaction. How many of you do remember the Friedel-Crafts reaction? As again, it's actually 11th standard concept, right? So what exactly is the Friedel-Crafts reaction? We take the benzene ring, correct? I'm just going to go with the normal Friedel-Crafts reaction. We take the benzene ring, then we go with the CH3Cl, correct? Methyl chloride. So this guy is what here now? This guy is a methyl chloride. Okay, and here is the benzene ring, and then the whole reaction takes place in the presence of a catalyst. So let me take a catalyst AlCl3. What exactly happens now here? The benzene ring gets attached with what? The benzene ring gets attached with the CH3. So we are producing what here? We are producing a methyl benzene, or more commonly I can call this molecule as what? I can call this molecule as a toluene, correct? Now this Friedel-Crafts reaction is governed by certain groups if they are initially present on the benzene. Okay, so there are 2 types of groups. Normally when I speak about the groups, there are 2 types of groups. One we normally call it as what? One we normally call it as an electron withdrawing group. Electron withdrawing groups. And there is another set that is called as an electron donating groups. Electron donating groups. Okay. Now, what is the function of the electron withdrawing group? What is the function of the electron donating group? Many of them have answered 4. Yes, it's a perfect answer, but let us try to understand the concepts. Okay. I am very much happy that everybody are answering. That's very good. Okay. Electron donating group and the electron withdrawing group. Okay. So what exactly they are doing? Okay. Electron donating group increases the electron density. See, it's finally what? If you check the Friedel-Crafts reaction, which category of a reaction it is? Which category? It's an electrophilic aromatic substitution reactions, correct? Electrophilic. Sorry, electrophilic substitution reactions, correct? That means an electrophile. So here what exactly happens now? The CH3Cl first reacts with the AlCl3 and is going to produce what? Is going to produce a CH3 plus ion, plus there will be an AlCl4 negative. Yes, it's an ESR reaction, electrophilic substitution reaction. Very good. So you see there is a carbocation formation, correct? Which is nothing but what here? Which is nothing but, I can call this guy as an electrophile, correct? Which is nothing but the electrophile here. Correct. Now this electrophile is getting substituted at the benzene for the expense of one of the atom here. Correct. So now what exactly happens? If there are electron donating groups, they are going to increase what? They are going to increase electron density. Correct. They normally increase the electron density on benzene. Correct. If the electron density on the benzene is increased, this is going to favor what? This is going to favor ESR reaction, electrophilic substitution reactions. So it is going to favor the ESR reactions. Okay. But in case if there are electron withdrawing groups, normally what we say is they are going to decrease the electron density. They will decrease the electron density because they're electron withdrawing groups, right? They are actually pulling out the electrons from the benzene. So electron density is decreasing on the benzene. Okay. On the benzene. So what exactly happens? Less favorable, correct? So these becomes less favorable towards what? Towards the ESR reaction. Sorry. Less favorable towards the ESR reaction. Please make a note of it. Okay. Less favorable towards the ESR reactions. So I understand over here that the nitrobenzene, the nitro group is actually a what? NO2 group. So here the NO2 group is what? It is actually one of the strongest, I mean, it is the strongest electron withdrawing group. If you see the categories over there, it is the strongest electron withdrawing group. So what exactly is happening? This guy has a least tendency or a group which will not favor what? Which will not favor Friedel-Crafts reaction. Please make a note. Which will not favor Friedel-Crafts reaction. Please write down the things. I'll give you 20 seconds. Be quick. Please write down the things. Okay. Now, it is also very important to understand the individual structures over there. Okay. It is also very, very important that you understand the individual structures. What is that xylene structure? What is the toluene structure? What is the cumin? Toluene I've already written there. It's nothing but the methyl benzene, correct? It is nothing but the methyl benzene. Who can give me the toluene structure? You have some time. Come on, give me the cumin and give me the xylene structure. Be quick. Cumin is a very, very well-known molecule, right? Cumin is a very well-known molecule. Can anyone tell me where exactly the cumin is actually used? Cumin is actually very well used for the preparation of a phenol, correct? If you remember the chapter. So, okay, fine. So toluene I have already given. Xylene is what? Presence of two methyl groups. Again, there will be orthoxylene, metaxylene, paraxylene, all those things. So here you have a CH3, and let me say I have also written a CH3. So it is nothing but the orthoxylene. So two CH3 groups is xylene. Okay. Cumin is what? I'm going to write it here. Cumin. We have a benzene group. We have a benzene group. On this, we have a CH attached with how many CH3 groups? Two CH3 groups. So this is our cumin. Cumin. Please write down the molecules, which are again very, very important. Cumin. Right. So we are going to move on to the next question. Right. Which one is most reactive towards nucleophilic addition reaction? So think of a reaction. It's a nucleophilic addition. It is not a substitution. Nobody is getting substituted here. It is purely what? It is purely just addition reactions. Okay. So how do you explain? Okay. Now, let me say I have a benzene ring over here. Nucleophilic addition is what I'm speaking. Then you have a carbonyl group over here. Okay. I'll just keep it like this. Carbonyl group over here. Now, when you see that carbonyl group, you clearly understand. See, when I say this carbonyl group is present, C double bond O, oxygen, if it is present, what is exactly happening now? Because of the inductive effect in this particular molecule, oxygen being more electronegative compared to the carbon, this guy always have a tendency of getting a partial negative charge. This guy always has a tendency to get a partial positive charge. Correct. That means he is actually developing which character? He is actually developing the electrophilic character. Correct. Electrophilic character in the sense electron deficient character. This guy is actually developing. Correct. The carbonyl carbon. We call this as a carbonyl carbon. Correct. So if this carbonyl carbon has a tendency to develop the partial positive character. So if I have a nucleophile, this nucleophile is what? It is actually an electron rich center, correct? It's an electron rich center. It always seeks, it is always seeking what? It is always seeking an electron deficient center, correct? It is always seeking an electron deficient center. So what is this nucleophile going to do? This nucleophile has a tendency to attack this electrophile. Correct? The nucleophile has a tendency to attack the electrophile. So this is what I was speaking about, nucleophilic addition reaction. Nothing is getting substituted here. So this double bond goes over here. This is what is exactly happening. Everything is going to add here. The nucleophile is going to add. Now, which of the following molecules, read the question now, which of the following molecule is most reactive towards nucleophilic addition reactions? Correct. Now, when can this carbonyl group be most reactive? That is the question, correct? When can this carbonyl group be most reactive? Simple question, correct? Greater the partial positive charge. Okay, so I'm just going to write a point here. Greater the partial positive charge. Greater the partial positive charge. Greater is what? Greater is reactivity. Greater is reactivity towards the reaction. Towards the reaction. Which reaction we are speaking about? We are speaking about the nucleophilic addition reaction, correct? Please, can anyone give me the answers? So many were answering. Superb. Can anyone give me the answer? Shobhit, Shubhadev, so many are there. Please give me the answer. Anyone who can give me the answer? Greater the partial positive charge, greater is the reactivity towards the reaction, correct? That means more and more, if you increase the positive charge on the carbon, the nucleophile is going to easily attack on that, correct? Now, who can increase the positive charge? Who can increase the positive charge? Somebody who has a, so who can do this? Okay, who can do this? Greater positive charge, who can develop it? It can be developed by which group? It can be developed by electron withdrawing group, correct? It can be developed by electron withdrawing group. Electron withdrawing group can develop more and more partial positive charge on the carbon, correct? Yes, withdrawing group, very good. So if you see now here, if you see the CH3, what is the CH3? CH3 is an electron donor. Okay, is an electron donor. If you see the NO2 group over here, what is this guy? This guy is electron withdrawer. This guy is an electron withdrawer. That means all the electrons are actually coming in which direction? They are coming towards the NO2 group. That means this particular carbon becomes more and more what here? Becomes more and more positive charge, partial positive charge, so that the nucleophile can attack this particular carbon much easily. Can attack much easily. Now, what is the problem with the second example? What exactly is the problem with the second example? If you see the second example, I've just written here. Okay. Now you see there is a partial positive charge and you see there's a partial negative charge. Don't forget there is a CH3 group, which is actually what? Which is actually an electron donor, correct? There is an electron donor. So because the electron donating group is present, the partial positive charge, what happens? It is going to decrease. Partial positive charge decreases. Okay. So according to that, and according to the concept, what we have just learned now, what should be the perfect answer? The perfect answer has to be the fourth one. Which one is the most reactive towards the nucleophilic addition reaction? Electron withdrawing, a molecule bearing an electron withdrawing group has to be more reactive. It has to be more reactive. Okay, right. Let us go for the next one. Let us go to the next question. This is a nice, interesting question. Again, the question is based on what? The question is based on the Friedel-Crafts reaction. The question is based on the Friedel-Crafts reaction. You get 30-40 seconds. Start. You have 30-40 seconds to solve it. Please start solving it. Now, if you just remember, we solved a question based on the Friedel-Crafts reaction, right? We just solved a reaction based on the Friedel-Crafts reaction. And I told you very clearly that in the Friedel-Crafts reaction, if you check this particular part, I told very clearly that there is a formation of what here? There is a formation of a carbocation, correct? There's a formation of a carbocation. That means a Friedel-Crafts reaction will follow, a pathway where a carbocation is definitely formed. Okay. So now you have to think among these four, who is actually able to form a carbocation? Who is able to form a carbocation? So now let me say a reaction. So let me say there is a benzene. I'm doing the Friedel-Crafts reaction. Okay. Then you are going to take the Rx guy, or let me say the ARX guy. And this guy is reacting in the presence of AlCl3. Okay. So what is the step one in the reaction? The step one is always the Rx guy or the ARX guy reacting with which one here? Reacting with the AlCl3. Let us not forget that this guy is actually what? This guy is actually an Lewis acid. That means he's having an electron accepting character. Very important point again, electron accepting character. Okay, Lewis acid is an electron accepting character. So now in the first step, what exactly happens here? Rx or ARX reacts with AlCl3. The X guy gets combined with what? AlCl3, giving you the R plus, the carbocation, and along with that there will be AlCl4 negative charge. Okay, AlCl4 negative charge. Now the whole question comes here is, when the reaction is following a carbocation formation, you just need to check which of the following is forming a stable carbocation. Again, that stable carbocation or forming a carbocation is a very important step in this particular reaction. Okay, so he is going to form the stable carbocation. Now let us do a reaction one by one. See here now, if the ARX guy, okay, if the ARX guy reacts with the AlCl3, he is going to form what here now? He is going to form the AlCl4 negative, and he is also going to form an Ar positive charge. Correct? He is going to form a phenyl cation. So please make a point. He is going to form a phenyl cation. Okay. Now, if you check the stability order of the carbocations, if you're checking the stability order of the carbocations, phenyl cation falls in the category of least stable carbocation. Okay, along with least stable, the phenyl cation, there's also one more category, that is vinyl carbocation. He is also the least stable, the vinyl cation. Okay, so you might have come across the vinyl chloride, right? So if you write this chloroethene structure, the structure will be what? CH2 double bond CH2, then you have a Cl over here, correct? So if you remove this Cl, if the Cl is departing from the vinyl chloride, I mean the chloroethene, it is going to form here what? It is going to form the, sorry, it was CH2CH, okay, not CH2, okay. So this is your vinyl chloride structure. So if you depart the Cl from here, so what is going to happen? It is going to generate a positive charge, okay, a vinyl cation and a phenyl cation. Now you have to understand both these cations, the vinyl cation and the phenyl cations. These are falling in the category of what? Least stable carbocations. They are one of the least stable carbocations. So forming such kind of carbocations is very, very less favorable. Very less favorable. Okay. But if you check the isopropyl chloride, okay, if you check the isopropyl chloride, what exactly is happening? How many of you can give me the isopropyl chloride structure? Okay, how many of you can give me the isopropyl chloride structure quickly? So if you check the structure isopropyl, you have a CH3, you have a CH, then you have a CH3 and a Cl over here. Okay, so this is what? This is your isopropyl chloride structure. Okay, now this guy produces what? This guy produces a cation CH3CH with a positive charge and a CH3 over here. So it's actually producing a stable carbocation compared to the others. Compared to the others, he is producing the stable carbocation. That means this guy has a greater tendency to undergo what? This guy has a greater tendency to undergo Friedel-Crafts reaction. So please make a note, this fellow. Okay, many of us, yeah, most of them have given the answer. Very good, superb. So isopropyl chloride. And also you have to remember when you're doing the SN1 and SN2 reaction, especially at the NEET level, you should also understand that where is rearrangement possible, whether in the SN1 or SN2, where exactly the rearrangement is possible. Okay, that's also a very important factor, because when you are solving a competitive exam, you should be knowing it. Okay, competitive exam questions. Right, let us move on to the next question. Let's go to this question. Nice, interesting question. Again, this has been picked from one of the previous year papers itself. Okay, right. You have 30-40 seconds to solve the question. You have 30-40 seconds to solve the question. Anyone who can give me the answer? Be quick, guys, be quick. Anyone who can give me the answer? Right, so let us solve this question. Okay, now how do we identify what is the initial molecule? C7H8, then you have a 3Cl2 and heating, right? See, again, there are different techniques, or see, it all depends on which technique you are comfortable with. The first thing we should be knowing is the general formulas of the hydrocarbons. So we have come across the alkanes, right? We have come across the alkanes, we have come across the alkenes, we have also come across the alkynes, correct? So we understand here it is CnH2n, correct? Then we also come across this CnH2n minus 2, and here we come across CnH2n plus 2, correct? So if you apply these formulas to the initial compound, this compound will not obey any of the rules, any of the general formulas. So what I do understand here, it is neither an alkane, neither an alkene, neither an alkyne over here. I clearly understand. Okay. Now, if I want to predict this molecule, how do I predict it? Okay. How do I understand what is the initial molecule? The simple way, again, I'm telling you, right? It all depends on individual's method. Okay. Some other may tell you some other method. So it all depends on the individual method. The simplest way to identify what is the initial molecule, what exactly it contains is, look at the answers option. In the answers option, if you check, everywhere you see there's a toluene. Here also you see there's a toluene. Here also you see there's a toluene. Here also you see there's a toluene. So what I clearly understand is that the molecule should have what? Should have a benzene ring and a toluene, correct? Benzene ring with a CH3. Yes, Ram has given the answer. We will check whether Ram is correct or not. Okay, no issue. So the initial molecule is definitely having a benzene. So how did I identify whether it is having a benzene ring or not? By checking the answers option. Okay, the options which are given in the question. Everywhere they are mentioning it's a toluene. That means I clearly understood there is a benzene. Okay, now even if you check this molecular formula, this is what this is. You have here 6 carbons, and then the top carbon you have a 7 carbons. Don't forget there's a hydrogen, there's a hydrogen, there's a hydrogen here, there's a hydrogen here, and the hydrogen here. So the formula will be what? It is going to be C7H8 formula, correct? So I clearly understand that the initial molecule is definitely what? The initial molecule is definitely toluene only. The initial molecule is toluene only. Now we will try to understand the reaction. Initial molecule is no doubt the toluene having a CH3 group on top. Now, if you are doing the chlorination, 3 molecules of Cl2 and you are going to heat. See, you have to understand, radical reactions are possible either in the presence of what? Either in the presence of light, or in the presence of what? Or in the presence of heat. This I think we have already studied, right? If you remember your 11th standard chlorination of a methane. Chlorination of methane is a very well-known reaction, correct? So if you remember the chlorination of methane, so we clearly understand that if we have to do the radical type of a reactions, we have to go to what? We have to go for using either the light, or we have to go for using the heat. Either the light or the heat, correct? So what exactly is happening over here now? If I react 3Cl2 in the presence of heat, side chain alkylation takes place. Side chain chlorination takes place. Sorry. So here I see there is a side chain chlorination. So which is the side chain over here? CH3 is the side chain, correct? So I understand here side chain chlorination. Okay, so 3 molecules of Cl2 means what exactly happens here now? -3 times HCl is going to happen, correct? Remember your chlorination of methane reaction. That is the best reaction you can remember, correct? -3 HCl. So what exactly is going to happen now? At the place of 3 hydrogens, you will end up getting 3 Cl molecules, correct? So you will have a CCl3 molecule. Okay, now the CCl3 molecule, it is very important for you people to understand what kind of a group it is. Okay, what is this CCl3 molecule? I mean to say whether it is an electron donor or whether it is an electron withdrawer. Electron donor or electron withdrawer. So what exactly is going to happen if it is an electron donor, or what is going to happen if it is an electron withdrawer? So based on the groups which is already present on the benzene, the incoming electrophile is getting its position, correct? If it is an electron donor, the electrophile which is going to attach to the benzene goes to which position? Goes to either the para position or it goes to the ortho position. Again, 11th standard chapters, very, very important. Okay. If it is an electron withdrawer, then the electrophile goes to which position? Electrophile goes to the meta position. Okay. So if it is an electron donor, the electrophile goes to a para or ortho position. If it is an electron withdrawer, the electrophile goes to what? Electrophile goes to the meta position. Okay. Now, if you check the CCl3 molecule, interestingly, it is what? It is actually an electron withdrawer. Okay, it's an electron withdrawer. That means the incoming electrophile will go to which position? It is going to go to the meta position. Okay, so what exactly is going to happen now? What is going to happen? So just give me 1 minute. So if I do the bromination in the presence of Fe, in the presence of iron, so here what happens here? Bromination in the presence of Fe, okay, Br2 in the presence of Fe. Now the Br will go to which position? Will go to the meta position with respect to CCl3. with respect to CCl3. Am I clear? Because CCl3 is what? CCl3 is actually an electron withdrawer. So he will push the electrophile to which position? He is going to push it to the meta position. So this is your meta position. Okay. Finally, what you're going to do? You're going to do the zinc with HCl hydrolysis, correct? That means you're going to remove all the, you're going to remove all the chloride molecules from there. Once you remove them, so what is going to happen now? You will end up getting, so this is your benzene ring. Still the Br is attached, and now in the place of Cl, CH3 comes and attaches. CH3 comes and attaches. So very good. Shobit has given the third option. So what is the name of this? This is metabromotoluene. Metabromotoluene. So you will end up getting the answer as what? The answer is the third option. Super. Please write down the reaction. I'm going to give you 10-20 seconds. Okay. So the answer is the third option. Yes, Manoj. So many of them are giving right answers. Thank you so much for giving the right answers. Also, when you are writing down the questions, I mean, the questions are available for you on the internet. That's not an issue, but it is very important that you note these small concepts, okay? So that you can easily practice the questions next time when you are solving them. Right. Let's go to this one. Order of reactivity towards electrophilic substitution reaction. We have already understood few things, right? Electrophilic substitution reactions. Who is going to increase the reactivity? Who is going to decrease the reactivity? We have already understood. An electron donor. Okay, it's an electrophilic substitution reaction, correct? It's an electrophilic substitution reaction, correct? So electron donor increases the reactivity. Electron donor increases the reactivity. Electron withdrawer decreases the reactivity. Decreases the reactivity. And also you have to understand that the resonance effect, okay, is a much stronger compared to which effect? Compared to the inductive effect. Okay, it's an important point. So whenever I'm solving a questions based on this, I will tell you how to use them. Okay, so don't worry about that. You just make a point that resonance is a much stronger effect compared to what? Compared to the inductive effect. Okay. Right, you have 30-40 seconds time has started. Please be quick. Right. Now, first, let us categorize each group and what are their effects. When you take the OCH3 gives you the plus R effect. So plus R effect means he's an electron donating group. Okay, so he's an electron donor. Cl also has a tendency of a plus R. CH3 also has a tendency of plus R. That means they all have a tendency to donate the electron. I mean, they are electron donating groups. So they all are giving you the positive resonance. Okay, plus resonance. But let us not forget that this guy gives plus I, he is going to give you the minus I, he is also going to give you the minus I. Okay. Now, when you go to the NO2 group, he will give you the minus I and is also going to show the minus R effect. That means he is an electron withdrawer. Please write down these things. As I told you, everything is important. Electron withdrawer. Okay. So what I do understand here is, a group with electron withdrawer has to be the least reactive, no doubt in that part. Okay, that means the third guy, okay, the third molecule with an NO2 group has to be the least reactive. There's absolutely no doubt in it. So first let me write it. Okay, so 3 has to be what? 3 has to be the least reactive. But now the question comes, everybody is showing you the plus R. All of them are what? All of them are actually an electron donating group only. From the three, if you check, all of them are actually electron donating only. But who is a stronger electron donating group is now the question mark. Who is a stronger electron donating group? That means that is why I told you resonance effect has a greater effect compared to what? Compared to the inductive effect. Okay, resonance is much stronger compared to what? Compared to the resonance. So what I do understand here is your OCH3 group is more effective. Please give me 1 minute. Okay, the OCH3 group is much effective than compared to the CH3 than compared to the Cl. Okay, this is what? This is the strength with respect to their plus R effects. Strength with respect to plus R effects. Okay, so now you think, if this is your plus R effect, okay, which should increase what? Which should increase the reactivity. What should be the order? What should be the order? So 3 has to be the least reactive. Then comes the Cl guy, correct? Then comes the Cl guy. Then the reactivity goes on increasing with the 4th guy. Okay. Then the reactivity is the highest with respect to what? With respect to OCH3. With respect to OCH3. So 3, 2, 4, and 1. 3, 2, 4, and 1. 3, 2, 4, and 1. Hope the writing part is over. Anupriya, correct answer. Thank you so much. Last one. Okay, let us go for this question. Just give me 1 minute. Right, we'll start with this one. Okay, nitration. We'll start with the nitration. How many of you can answer this question? How many of you can answer this question? How many of you can answer this question? Nitrobenzene can be prepared from benzene using a mixture of HNO3 and H2SO4 in the mixture. Nitric acid acts as an, you can see it is an AIPMT 2009 question. So nitric acid is acting as what exactly here? Whether it is acting as a catalyst, whether it is acting as an acid, or whether it is acting as a reducing agent, or whether it is acting as a base. Your time starts now. Your 30 seconds starts now. Okay. Who can answer this question? Your time has started. Shobit has given the answer. He's telling his base. But I would also like to know, how did he decide it is a base? How did he come to know it's a base? Subhadeep is telling it is A, it's a catalyst. Think once again, okay? So how did you see? If you open your NCERT textbooks, they have, I think they have given the nitration mechanism. If you go there in the NCERT textbook, or if you go to some of the reference textbook, understanding these mechanisms is very, very important, because at the competitive level, so you can see this question, if you know the mechanism, you can understand it properly, right? So going through the NCERT becomes very, very important. So now let us try to understand what exactly is happening. So first thing is what I'm going to write the nitration reaction. What exactly happens in the nitration reaction? So we have a benzene ring over here, and they are going to react with what? Is going to react with concentrated H2SO4, and there is a concentrated HNO3, correct? Concentrated HNO3, and we end up getting what here? We end up getting a benzene having an NO2 group. That means what? This is our nitrobenzene, correct? This is our nitrobenzene. But as I told you, understanding the mechanism is very, very important. So what exactly is happening here? Okay. See, let us not forget that again, these are the category of ESR reactions, correct? These are the category of ESR reaction. That means electrophilic substitution reaction. So in this reaction, if you say, okay, there should be a generation of an electrophile. There has to be a generation of electrophile, and that electrophile is what? NO2 plus ion, nitronium ion. Please make a note. There's a generation of a nitronium ion. Similarly, if you go to the, see, this is nitration reaction. This is a nitration reaction. If you go to the sulfonation reaction, there's also one interesting question. In the sulfonation reaction, what is an electrophile? So you can take it as a homework. In the sulfonation reaction, what is an electrophile? So normally, whether it's a neutral electrophile or a charged electrophile, because if you see this guy, if you see, he's a charged electrophile, positively charged electrophile, right? So this guy is a positively charged electrophile. So if you go to sulfonation reaction, you have to understand whether the electrophile, what is forming there, whether it's a charged electrophile or a neutral electrophile, and also what is the structure. So all these things you have to understand. Okay. So let us try to understand how this electrophile or how this nitronium has actually been generated. Okay. So if I write the structure, N double bond O, then we have a coordinate bond oxygen, then we have an OH. What is this? This is our HNO3. Okay. HNO3 starts reacting with H2SO4, sulfuric acid. Okay. S double bond oxygen, then you have an OH over here, then you have a OH over here. So this is our sulfuric acid structure, H2SO4. Now it is very common, we know that H2SO4 is more acidic compared to HNO3. Everybody knows this, correct? H2SO4 is definitely, so generally if we speak, H2SO4 is slightly more acidic compared to what? Compared to the HNO3. So what exactly is going to happen now? Let us not forget the definitions, common simple definitions of acid and base. If I say an acid, he should always what? He should always donate the H plus ions, correct? Now, when I say a base is the one who should normally accept the H plus ions. Okay, an acid is the one, he should donate the H plus ions, and the base is the one who should accept the H plus ions. So here what exactly happens is, the proton of the sulfuric acid and the OH of the HNO3 gets eliminated as minus H2O. Okay, it gets eliminated as minus H2O. So what do I understand here now? Yes, I think now you people are getting the concepts. So what do I understand? Sulfuric acid donated proton, correct? Sulfuric acid donated proton, HNO3 accepted proton. Sulfuric acid has donated a proton and HNO3 has accepted a proton. So if this part is removed from here, what is going to happen now? N double bond oxygen and a coordinate bond oxygen, and nitrogen gets a positive charge, which is nothing but your nitronium ion. So according to the mechanism what we have just seen, or the reaction what we have just seen, I clearly understood that the HNO3 is actually acting as what here? It is actually acting as a base. Hope there is no confusion now. Okay, right then. So we are going to stop the class. If you have any doubts, please let me know. Please subscribe, please share with your friends. Okay, I will be doing some of the organic chapter sessions. Okay, nice questions we will try to discuss. Right then, thank you so much. Good night, everyone.